Hello, Matthews Gatos here. Now that you've gone through and done an introduction to related rates and how to take the derivative with respect to time, I want to get into part one of related rates, which I call equation type problems. So in these types of questions, we're going to have some sort of an equation representing the situation. Might be volume, might be surface area, etc. So what we're going to do is we're going to assign variables to all the given and needed quantities. And I always find it useful, if possible, to sketch a diagram just so I can visualize what's going on. Now, I want you to only use variables whose rates of change are either given or needed. So sometimes, even though a formula has 3 variables, we only have rates of change for 2 of them. So I want to write the third variable in terms of the other 2 variables. So once I have everything set up, and remember, there's only one thing I can't know. So once I have my equation all set up, I'm going to implicitly differentiate both sides with respect to time. Now, I'm going to do that before I substitute any numbers in. As soon as I take the derivative of both sides with respect to time, then I can substitute all my values into the equation and solve for what I am needing. So remember, if a variable is decreasing in size, we have to accompany that with a negative. If it's increasing in size, that is a positive value. So again, to recap, here's my steps. I'm going to identify all my unknowns, remembering only one unknown is allowed, state my formula, derivative with respect to time, substitute everything in, isolate for the quantity that I want, and don't forget to answer with units. So I'm going to take you through 3 different examples. Okay, in example number 1, we have a spherical snowball melting in such a way that the volume is decreasing at a rate of 1 centimeter cubed per minute. At what rate is the radius changing when the radius is 5 centimeters? So what I like to do on the side is just kind of read that again and label all my variables. So first thing that we're given is the rate of change of volume. So I know that dV by dt, it is decreasing, meaning negative 1. I'm given the radius is equal to 5, and I want to know the derivative of the radius with respect to time. Those are the things that I do not know. So I want to look at my formula and see if I'm good. So I have volume, and I'm going to take the derivative with respect to time, so I'm good there. I have radius, I know the radius, and I know the derivative with respect to time. So it looks like I'm good to go on this question. So what I'm going to do is take the derivative of both sides of this equation with respect to time. So let's write out the equation, and then away we go. So the derivative of volume with respect to time is dV by dt. Now 4/3 pi, that's just a number. So I'm just going to write that up front, 4/3 pi. And then I'm going to multiply that by the derivative of r cubed. So again, if you have a constant, you can always take it out front. Just like we did for limits, we can do the same thing for derivatives. The derivative of r cubed is 3r squared, and of course times by the derivative of radius with respect to time. So now that I've done my derivative with respect to time, I can just substitute in all my known values. So the derivative of volume with respect to time was -1. That will be equal to 4/3 pi multiplied by 3 times the radius, which is 5 squared. And then we have our unknown quantity, dr by dt. Okay, so we have -1 equals 2. Now, 3 multiplying by 3 and dividing by 3, those are gone. So I'm left with 4 pi multiplied by 5 squared is 25, dr by dt. So just one more step here to simplify that before we isolate for our variable. So I have -1 equals 4 times 25 is 100 pi times by dr by dt. So to solve for dr by dt, I'm going to divide both sides by 100 pi. So -1 over 100 pi is equal to dr by dt. So I've isolated my variable. Now I just have to answer with units. So what I would say is that the radius is changing at a rate of -1/100 pi centimeters per minute. So in other words, as the volume gets smaller, so does the radius by that rate. Okay, that's a nice, simple first question where we had everything that we needed and we didn't have to rearrange any formulas. Let's look at another example. So in this one here, we have a water tank that's built in the shape of a right circular cone. It has a height of 5 meters and a diameter of 6. Notice I labeled it as a radius of 3. The reason I did that is because in my formula, I have radius, not diameter. Okay, now that's the physical structure. So 3 and 5 are constant. These are not changing because this is the structure of the cone. So we can't change the physical structure. What's going to be changing is the water level. Okay, so water is being pumped into the tank at a rate of 1.6 meter cubed per minute. So that means that the volume of water is increasing. Determine the rate at which the water level is rising when the water is 2 meters deep. Okay, so let's identify again what we have. So reading this again, the physical structure, we're not doing anything with that, that's not changing, but water is being pumped into the tank at a specific rate. So that's my volume. So I know that the rate of change of volume with respect to time is 1.6. So when I take the derivative of both sides, I've got volume covered, okay? Now we have radius and height left over. So let's see what we have here. So we want to determine the rate at which the water level is rising. That's dH by dt. And that is going to be when the height is 2 meters deep. So notice we don't know R and we don't know dr by dt. Well, there's only one thing that I'm not allowed to know. So what that means is that I can't have an R in that equation because I don't know what R is and I don't know what the rate of change of the radius is with respect to time. So what I want to do is come up with a new way of writing radius only using height. And the way that I'm going to do that is with similar triangles. So these triangles here are similar. On the inside, I have this big triangle, and it is similar to the little triangle made from the water. Similar triangles are triangles where the sides are in proportion and all the angles are equal. So I know that in my big cone, the radius of 3 is to the height of 5. So that proportion will also be true for the little triangle. So the little triangle, the radius is also to the height at that same proportion. Now notice I listed the radius in the numerator, the corresponding height in the denominator, so everything matches up. So since I want to write radius in terms of height, I am going to just multiply both sides of this equation by height. So that's gone. So now I get radius is equal to 3 times h divided by 5. So in my volume formula, I'm going to use this new radius, so it will look like this. So volume equals 1/3 pi times r squared. R is now 3h over 5 squared times h. So let's tidy this up a bit. So volume is equal to 1/3 of pi. I'm just going to write that as pi over 3 times 3 squared is 9, h squared over 5 squared is 25 times height. Let's clean that up even more. So remember, the simpler you can write your original function, the easier the derivative will be. Okay, now I notice that I do have a 9 in the numerator, a 3 in the denominator. 9 divided by 3 is 3. So really what I have is 3 pi h squared times h is h cubed, all divided by 25. So what I have now is I have an equation only using V and H. So that fits the information that I was given right here, okay? So that's what I meant by if you have a variable you don't have information for, you need to write that variable in a new way. And that's what we did with the radius. We wrote it in terms of height. So now I can take the derivative of both sides with respect to time. So the derivative with respect to time of volume equals, and I'm going to write this as 3 pi over 25, my constant first, h cubed. So I can take the derivative of both sides with respect to time. So the derivative of volume with respect to time, dv by dt, equals constant up front, and then the derivative of h cubed is 3h squared multiplied by the derivative of height with respect to time. And now I'm at the point where I can substitute in my known values. So dv by dt is 1.6. 3 pi over 25 times 3 times height squared, height is 2, and then there's my variable, my unknown variable, dh by dt. Okay, to make this a little bit easier, since I have 1.6, which is a decimal, and I have fractions, I'm just going to write 1.6 as a fraction. So of course 1.6 is 16 over 10, which in lowest terms dividing by 2 is 8/5. So I'm just going to write this as 8 over 5. So 8 over 5 is equal to, and then let's tidy this up. So I have 3 times 3 is 9, times 2 squared is 36. So I have 3 times 3 is 9, times 4 is 36 pi over 25 times by dh by dt. So to get dh by dt all by itself, I'm just going to divide both sides by 36 pi over 25, or you can just multiply both sides by the reciprocal. That might be a little bit easier. So multiply both sides by the reciprocal, because then these cancel, and I'm just left with dh by dt equals to, on the other side, I just have to simplify. So 25 divided by 5 is 5, and 8 and 36 have a common factor of 4. So altogether, I'm left with 5 times 2 is 10 over 9 pi. And so that's the rate of change of my height. So it's positive, which makes sense because the volume of the water is increasing. So I can just say that the height is changing, and it's changing at the rate of 10 over 9 pi, and then I'll throw in my units of meters per minute. Okay, I want to look at a similar question, but this time I want to look at what happens when the volume is decreasing instead of increasing. So in this one here, we have wheat being poured out of a conical chute, conical meaning just cone. Now the chute has a depth of 2 meters and a radius of 3 meters. If the chute is being emptied at a rate of 100 pi centimeters cubed per second, determine the rate at which the height of the wheat is falling when the height of the wheat in the chute is 1 meter. So notice I'm hearing meter, 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 and centimeter. So I want to have a common unit for everything. So what I did is I changed it to the smaller unit of centimeters. So 2 meters for the height or the depth, I changed to 200 centimeters. And the radius of 3 meters, I changed that to 300. So I'm changing everything to centimeters so I have the same units. Now, just like the last question, the 200 and the 300 are constant values. So these are not changing. They are the physical structure of the chute. So let's read this again and just note what we have. So the depth and the radius, those are constant, so I don't need to worry about those. Now it says the chute is emptying at a rate, so this volume is decreasing, so it's being poured out. So in this case here, my volume is negative. So my change in volume, dV by dt, is equal to negative 100 pi. So the volume is changing at a negative rate. I want to determine the rate at which the height is falling. So dH by dt, I don't know. When the height is, and again, we'll change this to centimeters. So when the height is equal to 100 centimeters. So again, notice that I have a formula involving volume, radius, and height, but I'm only given information for volume and height. So once again, I need to rewrite R using H, and I'm going to do that again with similar triangles. So over here, I'm going to look at my proportions. So I know that the radius of 300 is directly proportional to the height of 200, meaning the smaller similar triangle, the radius is also in that same proportion of height because they are similar triangles. Again, similar triangles are triangles where the sides are in proportion and all the angles are equal. So multiplying both sides by H, that's gone. I get 300 over 200 H is equal to R. Or, more simply put, let's cancel dividing by 100. I have 3H over 2 equals R. So that is what I'm going to use in my formula in place of R. So I'm only going to have a formula with volume and height. So volume is equal to pi over 3 times radius, which is now 3 height over 2 squared times height. So volume equals pi over 3. 3 squared is 9, h squared over 2 squared is 4, times by the other height. So height squared times height is altogether height cubed. Okay, so simplifying this, 9 divided by 3 is 3. So I'm left with 3 pi h cubed over 4 as the volume. And again, I can just write that so that the constant is up front. So volume is equal to 3 pi over 4 multiplied by h cubed. So at this point here, I have a volume only involving v's and h's, so I'm good to go. I'm going to take the derivative of both sides with respect to time. So the derivative with respect to time. So the derivative of volume with respect to time, dv by dt, equals constant up front. And then the derivative of height with respect to time is 3h squared, and then it will be dh by dt. So let's substitute in the values that we know. So back up here, just so you can see, we have dv by dt, negative 100 pi, and the height was 100, and we're solving for dh by dt. So volume, negative 100 pi, equals 3 pi over 4 multiplied by 3 multiplied by h squared, which is 100 squared. So 100 times 100, all multiplied by dh by dt. So I kind of wrote it out like that so I could simplify this a little bit easier. Okay, so let's start simplifying. So for example, if I were to divide both sides by pi, that would be gone. Okay, if I were to divide both sides by 100, that would also be gone. So on that side, I'm just left with a negative 1. Okay, on the right-hand side, is there anything else I can simplify? Well, 100 divided by 4 is 25. So really all I have left is 3 times 3, which is 9, and 9 times 25, which is 225. So I have negative 1 equals 225 multiplied by dh by dt. Divide both sides by 225, and I get negative 1 over 225 is equal to dh by dt. So it's negative as I expected because the volume is decreasing, therefore the height is also decreasing. So then I can just say that the height is changing, and it's changing at a rate of negative 1 over 225 centimeters per second. Okay, so I hope that that video helped you. I thought this was a really cute cartoon. If snow falls in a conical pile at a rate of, and it's going on, and the kid says, "Mom, do I have to go in?" It's relating rates out. So you guys can go ahead and do the practice questions. Again, this is part 1. So you can join me for part 2. And in part 2, we're going to look at triangle type problems. So I hope this helped, and I will see you guys for the next one.